son thought that was funny. He's in middle school. All right. So a pitcher throws a baseball. Hey, quit staring. Take a picture. All right. Throws a baseball, approaches the bat some speed. The bat does some amount of work on the ball and hitting it. This is interesting. All right. So if the ball is traveling this way, right, when it's pitched, okay, and then the bat hits it, all right, does a certain amount of work. Is there a positive, negative thing going on here? We have to worry about direction. We have to worry about direction when we're talking about energy. Why not? Because energy is a scalar. Nah. All right. So if he throws 140 kilogram, 100.140 kilogram baseball. All right. So look, we start off with we've got a mass and we've got a velocity, right? So we have some amount of energy, right? So now, as it's approaching, that's our energy. Is that really going to be our energy budget for the whole thing? Yes or no? How do you know? No. Because the bat does work on it, right? Look at this NC. That's non-conservative, right? All right. So we have a certain amount of energy to start with. That's kinetic energy, right? All right. And then to that, we're going to add the work done by the non-conservative force. And so what's that going to give us afterward? What's that give us afterward? A new amount of what? A new amount of energy, right? Because this is going to be a change in energy, right? All right, so we have some amount of energy. We add energy or subtract energy. Right here, here's the work done by the non-conservative force. All right, we're adding energy. All right, so now we're adding energy, and so later on we're going to try to find the speed when it's 25 meters above where it was before. So what is that going to be? It's going to be not only a change in kinetic energy, but a change in... Right. So this is our total energy budget for what the energy that it's going to have when it's way up in the air. Does that make sense? All right, so when it's up in the wild blue yonder, we're going to make it blue. We're going to have kinetic energy plus potential energy up there. All right? So this is doing all this, we're making the assumption that the initial level of the ball is H what? 0. Okay? So that's the initial level of the ball that's being pitched. Now we know the ball is actually going to drop. We can calculate that because we know so much about projectiles. But I think we're just going to assume that there's no significant change there. Okay? All right, so what's the kinetic energy to start with? Kinetic energy to start with is going to be equal to 1/2 mv squared plus the work done by the non-conservative force. We're just going to be able to put that in as a number. All right, it's going to be equal to, what's its kinetic energy up in the wild blue yonder? 1/2 mv squared. Now I'm going to go back over here and fix the same mistake I keep making. We're going to call that V naught. All right, 1/2 mv squared plus mgh. Now, one of the inconvenient things when we have work done by a non-conservative force is we can't just cross out all those m's, okay? Because it's not part of that term. So we're solving for the velocity, right? The speed of the ball after it leaves the bat, and then when it's 25 meters above the point of impact. All right, so actually I set this up to solve for the final question. So let's just solve for the beginning question, okay? The beginning question is, what's the speed going to be after this happens, okay? So the speed is going to be, we got 1/2 mv naught squared plus work done by non-conservative force is going to be equal to our new what? Kinetic energy. Good. 1/2 mv squared. So in this case, we're going to solve for that v. So we're going to say, here, let's go, 1/2, v squared is going to be equal, going to multiply everything by 2 over m. All right? We're going to say 2 over m times 1/2 mv naught squared plus work done by non-conservative force. We could mess around and cross things out and cancel things out, but let's just keep it simple. All right, so calculator crew. We got v is going to be equal to the square root of 2 over m times 1/2 mv naught squared plus work done by non-conservative force. So now let's go ahead and plug our numbers in. The velocity, the new velocity, going to be equal to the square root of 2 over 0.140 times 1/2 0.140 kilograms. Candygram. You guys never watch old Saturday Night Live, do you? All right. So what's our V naught? Initial V naught. Yes. Chevy Chase. All right. So what is it? Somebody told me to expand the equation. All right. So what was V naught initially? 25 meters per second? No. 40 meters per second. All right. So 40 meters per second, and that is squared, of course. And then we add the work done by the non-conservative force, which is 70 joules. That's just given to us straight. All right, so if we've got joules on the inside, see what I did? Yep, no, that's all right, that's all right. Because we're going to divide joules by kilograms, that's going to give us meters squared per second squared, right? So we're going to get joules inside here. I forgot to do this, right? Because we're doing this times all of that, right? All right. So, because that's going to give us, on the inside, it's going to give us joules. Kilograms meters squared per second squared. Oh, look what I did. Did anybody see that? Anybody catch me there? All right. I know. All right. All right, so now that we have all that, we're going to have joules inside parentheses divided by kilograms is going to give us meters squared per second squared. Square root of that's going to be velocity, okay? Just, it's a good idea to just do that mental checklist and get that dimensional analysis and make sure that you're on the right track. All right, so when we do all this mathy stuff, what do we end up with? 1.0? 1.0? Okay, good. 51.0 meters per second. All right, so that's the answer to A. Now, we could use that answer for A to find the energy budget, for above and, below, but we try to avoid using calculated numbers to do calculations based on them. So now we can just come all the way back to this, okay? If we come all the way back to this, and I'll just repaste that down here. Whoa. Come on. There it is. All right, so we're just going to go that'll be the B part B. Okay? So now we have kinetic energy, which is, to start with, 1/2 mv naught squared plus the work done by non-conservative forces is equal to kinetic energy 1/2 mv squared. And this is what we're looking for, to ask for the speed when it's way up in the air, right? Plus, oops, that should all be in blue. Now look what you've done. All right, this is what we're solving for. And we're going to add to that mgh. Okay? Still can't cancel out all those m's, dang on it. All right, because we still have work done by a non-conservative force. So now we're solving for this right here. So let's just take our v squared, and so we're going to subtract this. Here, watch this. I'm going to do this tricky way. All right. All right, so now. What? All right, now watch. So now we're trying to solve for this, so we'll take this, put it over here, and we're going to subtract this right here, right? It's going to be, we're going to take that, and then we subtract. That's going to be equal to, what did I take out? We'll fix that. All right, so now that's going to be equal to this. Now minus this, right? All right, minus that right there. Okay? That's an evil laugh, Mr. Culbertson. All right, so we got all that. Is that correct? So now all we got to do is divide by these guys right here. Divided by, what's going on here? There we go. Divided by that. Right? And then we're going to take the square root. Just try to keep track of all of them. So here, this is gone. All right, is that okay? All right, so it's a little bit weird with all those halves and things like that, and a math teacher would probably have a fit if we wrote something like that, but we're not solving it completely algebraically. We're just throwing our red pen around. All right, so we got 1/2. What's the mass of the ball? 0.140 kilograms. Times our initial velocity squared, which was 40, that's right, 40 meters per second. All right, we're squaring that, plus 70 joules, and then we're subtracting 0.140. We're running out of room. Plan ahead. All right. All right, 0.140. All right, that's mass times g. 9.8 meters per second squared times h, which was 25 meters. Is that correct? 25 meters. All right, we're dividing all of that by 1/2, 0.140 kilograms, and then we're taking the square root. All right, so up on the top, it should be all joules, right? This is joules. We can see dimensionally. If this is joules, everything else better be joules, or we can't add and subtract them. Kilogram meter squared per second squared. Check. Kilograms. He left it off. Kilogram meters squared per second squared. All right, so we got joules on the top divided by kilograms. Again, is meters squared per second squared. Square root of that meters per second. We're going to be in good shape for finding our velocity up there at the top. Okay? And by the way, what direction is its velocity going to be at the top? Straight that way, right? All right. So now, calculator brigade. What do we got here? What'd you say, Jason? 45.9 meters per second. All right. Is that sensible? Is it possible? What is the one thing that it can't possibly be? Can't be greater than 51. Good, Jason. All right, so as long as it's not greater than 51 and it's not negative, then we got to feel like we're somewhere in the ballpark. It's a reasonable answer. All right, so that is the answer, 45.9 meters per second. That was an extended video.